Welcome everyone. Today I'm going to present our paper Robust Asynchronous and Network Independent Cooperative Learning. This is a joint work with Eduardo Mojica and David Yanguas from Universidad Nacional de Colombia and me, Cesar Uribe from MIT. Traditionally, in distributed estimation problems, there are two main approaches. On the one hand, if we assume there is a fusion center, then all agents send information to this fusion center, and then they process the data in the centralized manner. On the other hand, if no fusion center is available, then agents need to talk to each other over a network in order to solve the distributed estimation problems. We will focus on the second kind. In particular, we want to develop an algorithm for which a network of agents try to agree jointly on a hypothesis that best describes the state of the world that is going to be revealed to them through observations or realizations of a random variable. And we are motivated by the widely applied methods in machine learning, social networks, decentralized control, and distributed signal processing that use these distributed estimation problems. And our challenge in this paper is to tackle harsh network conditions, in particular asynchrony, delays, and message losses. The problem setup is as follows. We have a network of agents, m of them from 1 to m, and each agent observes realizations of a random variable that is distributed according to some probability distribution pi, and this distribution is unknown. Moreover, each agent I has a hypothesis set about the probability distribution p sub I that is parameterized by a finite set theta. We will call distributions over this parameter space beliefs. Thus, every agent I has beliefs about the possible state of the world, and we will denote them as mu super I denoting the agent, sub k denoting time, and theta denoting the hypothesis. Thus, the overall objective is to solve the following optimization problem, which is to find the Kurbla-Leibler barycenter or the parameter theta that generates the distribution p of theta that is the closest to the true distribution of the observations. One can interpret this problem in the geometric form as trying to find a parameter theta that generates a probability distribution p sub theta that is the closest to an unknown distribution p, and in this case the triangle is the probability simplex. There is extensive literature studying this problem, where they analyze different types of networks, static or time varying, directed, undirected, and they prove consistency of the algorithms and asymptotic and non-asymptotic convergence rates. And here are some of the names of people working on that. However, we are interested in harsh network conditions, which we will describe next. We're going to assume the network or the graph G is strongly connected. Moreover, we are going to assume communications between the agents are delayed, and there is an upper bound in these delays. Every agent wakes up in an asynchronous manner, and there is also an upper bound on how many times this asynchrony each of the agents wakes up. Moreover, we're going to assume the links might fail, but there is also an upper bound on how many times this link might fail in consecutive times. And moreover, we assume that the message arrives in the order they were sent. So this is a rather flexible network model when we allow for delays, asynchrony, and packet losses. Our proposed algorithm has three main stages. On the one hand, each agent broadcasts local information to its neighbors. Then each agent that is waking up processes this information received and compares the timestamps. And then finally updates its beliefs according to some particular form that we will not describe. Our main result is as follows. We proved asymptotic exponential concentration of the beliefs around the true hypothesis. In particular, we show that each of the beliefs for all the agents concentrate around a theta that minimizes the optimization problem at a geometric rate asymptotically, and we characterize at the speed at which this concentration happens, which is proportional to the average distance between the optimal distribution and the second best distribution among all the agents. And this happens for all the agents at the same time, regardless of their observation model. Simulation results showed that our algorithm guarantees convergence in of all the agents in the presence of delays, asynchrony, and message losses. In this case, we see that the beliefs all concentrate around the true hypothesis. In this case, the yellow bar always converges to 1. And finally, we have proposed a method that is able to learn in a distributed manner with delays, asynchrony, and a general flexible network model. And our results show that all the agents are able to learn under this genetic learning model.